I think we'll look at the homework that we had over the weekend. Was worksheet number 7. 3 pages of it, all with 3 questions, 1 A, B, C, D, 2 A, B, C, D, and 3 A, B, C, D. I'll show you the answers here. Just take a quick peek at the answers as we scroll through them and let me know if there's any of those questions you need going over here. Question number 1, A and B. Give you a couple seconds for that. And then we'll take a look at C and D. You flip the page here and take a look at 1, C and D. Question number 2, A and B. 2, C and D up on the board here right now. Take a look at number 3 there now. And finally, have a look at question number 4. Already got a request to take a look at 1A, I think. You're good? Okay. Okay, so 1A is good. Any others? Patrick? The angle for number 4, okay. Yeah, okay, so let's take a look at number 4 in its entirety then, okay. Okay, number 4, going once, going twice. Okay, number 4 it is. Let's take a look at what the question is. It says, repeat question 2B above. I think it's 2B, is that what it says? 2B above, but with the first charge above the second charge. So let's look and see what 2B was. 2B said, find the net force on the second charge there. Let's see what we got here. The diagram for question 2B looked like this, where we had a positive charge, a negative charge, and a positive charge all in a row there. And I think it said, which one, the first charge was above the second one, did it say? What did it say there? The first charge above the second charge. So we're going to change that diagram now from this, which was 2B, to something like this. 1, 2, and 3 looking like this. Okay, number 1 and 2 are still 60 millimeters apart. Okay, probably a good idea to circle those units because those are a pretty non-standard unit there. We've got a distance between 2 and 3 of 5.0 centimeters. We'll circle that one as well. That's a little bit more common than we see millimeters, but in the end, that's still non-standard. We still want to convert those to meters. Number 1 has a charge of 2.50 times 10 to the minus 2 coulombs. This one is 4.0 times 10 to the minus 2 coulombs. Is that a negative? That's a negative, I think, isn't it? And number 3 is positive 3.00 times 10 to the minus 2 coulombs. Let's draw a free body diagram here for number 2. The force of 1 on 2. Well, they're opposite charges, so that's going to be an attractive force. That means number 2 is going to be pulled up towards number 1. F12 is upwards. 3 on 2, it's going to be pulling it to the right because, again, 2 is oppositely charged to number 3. F32 is going to be to the right. Let's calculate the values of F12 and F32. Now, the actual value of the force in F12 is exactly the same as it was in question 2B. And that's why this wasn't quite as much homework as it seemed to be, because there was a lot of repeat calculations like that. Let's take a look at what that force is here. 8.99 times 10 to the 9 times Q1, which is 2.5 times 10 to the minus 2 coulombs, times Q2, which is 4 times 10 to the minus 2 coulombs. Again, we're dropping the sign of the charge there. It's important for us to determine which way the force goes, but not in the calculation. R, 60 millimeters. 60 divided by 1,000 is 0.060 meters. Square that. And what do we end up getting for the force there of F12? Anybody have that? 2.4972 times 10 to the 9. Yeah. 2.4972 times 10 to the 9 newtons. So, Nick, you said 2.5 times 10 to the 9. Obviously, you're right on that one. Anya asked a question earlier on about rounding. okay, before our final answer. We want to go to 4 or 5 decimal places. There we've got 4. We should be pretty safe with that. If you use 2.5, you might get the exact right answer. Yeah, yeah. And it probably would work out in a case like that, but no guarantees, right? Travis, question? I'm sorry? No, because it's, if you divide 60 by 1,000, go do it on a calculator right now, 60 divided by 1,000. Did you see that? Okay. So if you're unsure about that, listen, that's one of my weaknesses too, is converting like that. And just doing things like that in my head. It seems like sometimes like such a simple thing. And the people that are good at it can't understand why people like you and I are like, wow, is it 0.06 or is it 0.006? Like it seems like such a simple thing. But on the other hand, sometimes some of us just aren't great at it. I'm not. Okay, maybe you're not. That's okay. Do it on your calculator. Okay, if you know the conversion factor is 1,000, go 60 divided by 1,000. Can't work for you every time. K is 8.99 times 10 to the 9. Q2 was 4 times 10 to the minus 2. And Q3 is 3 times 10 to the minus 2. The distance this time is 0.050 meters. Again, it's conversion from centimeters to meters this time. You got to divide by 100 instead of dividing by 1,000. What do we get for the value of F32 there? 4.3152 times 10 to the 8. Now that we've got both of those forces, let's draw our vector diagram. Don't confuse that with this. This is your free body diagram. Your vector diagram, it shows the forces, but it shows them adding them vectorially. So in other words, we have to draw them front to back or head to tail. The first vector, hey, that's F12. Let's draw that upwards this way, 2.4972 times 10 to the 9. The next one is 4.3152 times 10 to the 8. And we're going to find the hypotenuse there, and we're going to find the angle there. When we find the hypotenuse, the net force will end up being equal to 4.99 times 10 to the 9, using the Pythagorean theorem. And when we find the angle there, we're going to get 59.9. With the way that I have it drawn this time, it's going to be the inverse tan of 4.3 over 2.4. I'm going to get 59.9 degrees. Now, why, when I showed you the answer here a few minutes ago, why did I have an answer of 30.1 degrees? Because I drew the diagram the other way, right? I drew it x, then y. This time I drew it y, then x. Which one's right? Which one's more right? Either one of them are right, right? Doesn't matter which way you draw it as long as you draw it front to back. Okay, really what we're doing here when we're finding f is adding these vectors together. But you're not adding them together in the typical sense of adding, right? 1 plus, or 3 plus 4 is equal to 7. 3 plus 4 is equal to 7 is the typical way of adding, right? Here we're adding them vectorially where 3 plus 4 is equal to 5. Okay, so we're adding them together. Okay, when we add two numbers together, it doesn't matter what order we add them together, whether we go x then y or y then x. The old-fashioned way of adding, 3 plus 4 is 7, 4 plus 3 is equal to 7. Okay? So we add these two numbers together vectorially, x then y or y then x. We get the same answer. It may look different, but we get the same answer. Yep. I believe it's an 8. That's what I have there, at least. No, for F32 is... Oh, yeah. No, I think it must be a 9. I think it must be a 9 there. I think it must have made a typo there. Does anybody have that? It is 10 to the 9? Okay. So I think my answers are based on it being 10 to the 9 there. Probably this one was based on being 10 to the 8. I think I've just made a little typo there. Okay, so we'll make this 10 to the 9, but these answers still work out there, I think. Yeah. Thank you. Good? All right. Well, good news. You're on a bit of a roll here for doing lots of work. So let's give you a little bit more work, okay? Let's give you a little bit more work to do. Tonight's homework we'll give you right now is page 538. Page 538, some check and reflect questions. I want you to do the following questions on page 538, please. 1, 3, 5, 7, 9. 1, 3, 5, 7, 9. In other words, all the odds. Okay, got it? While we're at it, we might as well do the evens as well, okay? So let's do 1, 3, 5, 7, 9, and 2, 4, 6, 8, and 10. Get that? Sorry? Yeah, that would be it, yeah. Page 538, number 1 to 10. A number of these are not mathematical, so they should go relatively quickly for you. Not like 4 minutes quick, but not like 4 hours long either. Okay, let's move forward today. We've been talking about electric forces for the last several days. Today we're going to talk about electric fields. Just like we talked about gravitational forces in physics 20s and then went on to talk about gravitational fields. Okay, a lot of similarities between electricity and gravity, right? Okay, today we're going to learn about another similarity. A field is a line of influence that surrounds something. Any field is. Okay, this is not the definition of an electric field. This is the definition of any field. It's a line of influence that surrounds something. Now, gravitational fields surround objects with mass. Magnetic fields surround magnets. Electric fields surround electric charges, either positive charges or negative charges. They're vector fields. Okay, we call them vector fields because there is a direction associated with them. Okay, there is a direction associated with the influence. If I have an electric field pointing in one direction, a charge that experiences that field will be influenced in one direction or the other, a very particular direction. Unlike a scalar field, which influences something but not in a particular direction. We have a gravitational field, it always influences the mass downward toward the Earth or toward the producer. Okay, that's a vector field. If we have an electric field, the field always influences a charge in a particular direction. That's a vector field. If we have something like a light field or a heat field, light influences us, heat influences us, but not in a particular direction. So we'd call those both scalar fields. Now, what's the difference between a field and a force? A field is there no matter what. As long as you have something that causes it, the field is there. Talk about gravity for a second. The Earth causes a gravitational field. This board marker that I'm holding in my hand right now experiences a gravitational field. But it experiences the field that was caused by the Earth. If I take this pen away, the field is still there because the Earth that caused the field that the pen experienced hasn't disappeared. The pen is not there, but the Earth that caused the field is still there. So the field is there no matter what. As long as you have something causing it, the field stays there, whether you have something experiencing it or not. Having said that, the force only exists if there's something to experience it. You need a producer and an experience for a force. Okay, what's the field experienced by this pen right now? 9.81 meters per second squared. What's the force experienced by this pen? Well, the mass of the pen times 9.81 meters per second squared. If I take the pen away, what's the field at the point where the pen was? 9.81. What's the force at the point where the pen was? Well, there is no force because you can't multiply a non-existent mass by 9.81 meters per second squared. So in order to have a field, you just need to have a producer. In order to have a force, you need to have a producer and an experiencer. Same thing applies to electricity. Okay, if you've got a charge that causes a field, okay, then you're going to have the field no matter what. If you have something that feels it or experiences it, then you're going to have a field and a force. So fields exist as long as there's a producer. Forces exist only if there's a field and something to experience that field. Now, we said a couple of minutes ago that a field, this field, an electric field, is a vector field, so it has a direction associated with it. If it has a direction, we have to define that direction. The direction of a gravity field was simply the direction that a mass would move if placed in the field. In other words, downward toward the Earth or whatever the producer is. I put a mass in the Earth's gravitational field. Which way is it going to move? Downward toward the Earth. Therefore, the field is defined as being downward toward the Earth, the way that a mass would move if placed in the field. But in more than the electric field, though, this one's a bit trickier. And the reason this one's trickier than gravity in terms of direction is because with gravity, we have only one kind of producer. It's mass. With electricity, we have two kinds of producers. A positive charge, a positive producer, and a negative producer. So the direction is a little bit trickier. We define it arbitrarily as the way that a positive particle would move if placed in the field. We could have defined it arbitrarily as the way that a negative would move if placed in the field, but that's not the way it was done. The way that a positive would move if placed in the field. So, if you have a positive producer and you introduce a little positive experiencer right here, which way is it going to move? To the right. If we introduce a little positive producer or experiencer right here, it's going to move to the left, away from the positive producer. If we introduce a negative producer right here, and we put a little positive in here, positive experiencer, it's going to move toward the producer. Put a little negative in right here, it's going to move, sorry, positive in there, it's going to move toward the producer. So we define it as the way that a positive particle would move if placed in the field. Now remember, we don't have to actually put one there. Okay, which way would a positive producer move right here if I put it in the field? It would move away from it, right? Do I have to have one there? No, it's the way that a positive producer would move if it was there. It would move away from the producer. If I put a little positive experiencer right here, which way would it move? Towards it. Do I have to put one there? No. If I did put one there, it would move towards it. Therefore, the field is towards that producer. So the way that a positive particle would move if placed in the field, we can also define it as away from positive producer and toward a negative producer. And these two definitions really go together, right? I think the second one kind of flows from the first one. What if I put a little negative experiencer there? Which way would that go if I put it in the field? This negative is going to go which way? Away or towards it? Go towards it. Does that change the direction of the field? Which way is the field at that point? The field is still away from the producer. Even though the negative would go towards the producer, the field is still away from it. And that's because I define the direction as the way that a positive would move if placed in the field, not a negative. So in other words, positives will always move with the field, and negatives will always move against the field, or opposite to the direction of the field. Does that make sense? Okay, that's why it's a little bit trickier than gravity, right? Because gravity always, the mass always moves with the field, never against it like this. Let's take a quick look at a little applet that shows, don't have to copy this down, I'll draw some pictures in a bit here. just shows the direction of electric fields surrounding certain charges. Okay, if I put a positive experiencer anywhere surrounding this little positive producer that you see in the middle, which way would it go? Well, in the direction of the arrows there. Okay, I could put a million positive experiencers in there, and you would see at any point the field would point away from the producer. Okay, and that's exactly what you see there. Okay. Sometimes we kind of summarize, in a sense. The field lines kind of make them kind of look like this. But in the end, a more accurate representation of the field would be what you see without those red lines drawn in. Okay, because that shows a lot more places where the field acts, right? Where the field is. Let's try when we see two charges here now. Okay, that's a single charge, a positive. All right, let's put a double in there, two positives. What do we see here? Well, if I put a positive right here, it's going to go out this way, right? If I put a positive right here, it's going to go out this way. If I put one right here, it's going to go out this way. What if I put one right here? Well, it wants to go out this way, but what happens? Well, there's an influence going this way as well, right? So what do you end up getting? They kind of go around like this. They kind of push each other away, kind of repel each other. Okay, same thing on this side. So what you see is something that looks like this. Right here. So if you're, okay, so that's a good question, Tanner. If you were to have a charge literally right there in the middle, keep going with that. Would it move left or right? What's the answer to that question? It would explode. What's the field right smack in the middle? Organ? Zero. The field right in the middle is zero. In other words, there is no electric field. If there is no electric field, what's the value of the force in the middle experienced by that charge? Zero. And let's think about that for a second, okay? You get two charges, two producers. You got another experiencer right smack in the middle. What force does it experience? None, right? None. The forces end up balancing. The field is zero. There is no force. The forces end up balancing there. Okay. That is assuming these charges are the same values, right? Let's take a look at another one here. We call it a dipole now. Where we have a positive and a negative. Okay, here it looks a little bit different. Okay, put a positive right here. It goes outwards, outwards, outwards. Okay, outwards, inwards, inwards, inwards. What happens right here? This guy wants to go outward. This guy wants to go inward. What happens? The field lines kind of, instead of repelling each other like they did in the last diagram, they kind of join up like this. That make sense? Notice the field lines are still going from positive toward the negative, but the shape is completely different in the middle than what we saw in the last diagram. These fields that we've drawn here are all what we call non-uniform fields, fields that are not constant. When field lines are not parallel, they're non-uniform fields. Okay, we're going to see in a little while here fields that are uniform. Okay, field lines that are parallel, just not today. Let's draw just a couple pictures here. Basically what we just saw, but we'll draw them a little bit simpler. Here's a positive producer. The field lines go away from a positive producer. Here's a negative producer. The field lines always go toward a negative producer. These fields, by the way, just like gravitational fields, are what we call radial fields. They radiate around the producer. We got a dipole here, or a positive and a negative. It's going to look something like this. Oops. You don't have to draw every single one of those field lines that I have drawn. You just got to get the basic shape, right? The big thing here is right in the middle what happens. The field lines join up with each other because we've got opposite charges, positive and negative. Whereas if I have a positive and a positive, let's say, the field lines in the middle repel each other. And it's going to look more like this. Oops. See the difference there? How would that last diagram change if I put two negatives in there instead of two positives? Would the shape of it change? Not at all. What would change? The direction. The field lines would be pointing towards the producers, I should say, instead of away from the producers. Has what we said so far make sense? Good. We'll leave it there today. Leave it with the diagrams today, and tomorrow we'll go into a little bit of mathematics on electric fields, okay? Remember, you got your homework is page 538, number 1 to 10. Let's have that done for tomorrow, and then we'll continue on with this after we're done checking that homework tomorrow.